Another YouTube recommended video for you guys. Well, we'll use that description of it anyway, as of another video I've talked about when YouTube recommended bringing you guys in on my day-to-day life. So just a fairly simple bush that I'm making at the moment. It's just 32mm diameter, or 31.75, so the old 1 3/4. Has a 16.5mm hole through the centre and two M8 threads in there for some grease nipples to go in there. It just goes into this part here, and for the moment I'm doing the welding on it. The bush has always been my job, but the welding is sort of something that's come to me from the customers that they're a bit busy with what they're doing, so they've asked me to make the bush and weld it into this part, which is not too bad. It's a bit like overload work for me, so I don't mind that, to see how long that one lasts for. Hopefully it keeps going with any luck. But just the main reason I brought you here for was not so much to show you the parts, but to, as you probably read in the title, the U-drill or insert drill, depending on how you guys refer to it as. You have to excuse my dirty rag there. It's just an old rag that I use to drain the coolant out of the parts. That's what I'm standing on, and also that's why it looks pretty dirty. So I don't put out a nice brand new towel for you guys for the sake of the video, so I have to excuse that. But the U-drill, or as I say, getting back to the U-drill or insert drill, as some people refer to it as, is ideal, I suppose you could say, a way of drilling holes, more so for CNC, but I'm running on the manual lathe, as you probably read in the title, for those who read the title. But I'm just going to bring you over on the manual lathe now and just show you the setup, just talk about some of the, I suppose, positives and negatives. Every positive has a negative, and every negative has a positive, as I always like to say. So I'll talk about some of that with this U-drill. As you can see, I've been drilling some stuff already. Just coming back to this job today. I was doing some yesterday, had a bit of a clean up, and come back again today to keep going with it. 16mm U-drill. I think it's about 4 times D, or 4 times diameter. It's probably about as long as I probably want to go for that diameter. It's up to you guys how far you go, but they do have a tendency to still flex. They're not the hardest of steels. They do still wear, as you can probably see a few scratch marks on there when the swarf's coming out. The setup that I've had, as you've probably seen in the title for this video, U-drill or insert drill, I keep referring to. I'll refer to it as a U-drill, just makes it easier. But I've just got a coolant line ported in on the side here of a collet chuck in a Morse taper number 4 tailstock. I've converted the thread over from the standard BSP 3/8 to a metric thread. I can't recall what size it was now. I've done this a little while ago, but being this is not super hard as steel, but it is pretty tough. Obviously, tool holders are fairly high grade steel, so I had to cut that with a carbide tap. So I'm not going to buy a 3/8 carbide tap just to do one job. I'd probably never ever use it again. So it's just got a 10mm air hose coming in, so it's nice and flexible, so I'm coming in and out with the tailstock and just drilling those holes as we go through. It's the DS20 style U-drill, for those who are not familiar, Sandvik brand, which is mostly what I buy. Most of my stuff's Sandvik. The positives I'll show you shortly when we drill a hole with it, and then we'll talk about some of the positives. Negative, I suppose you could say, cost of buying the drill. 16mm drill, you'd probably pay, I don't know, for a normal twist drill, you'd probably pay, I don't know, depending on what dollars you're talking in or currency. So in my part of the world, possibly, depending if it's Morse taper or reduced shank, possibly around about the $50 to maybe $90, possibly. It might get up that high for the Morse tapers, for a good quality one. There is cheaper brands around, of course. This one's probably about 10 times that. That's probably the downside, and the inserts aren't cheap. I can't recall how much I paid for this one now. It'd probably be around about the mid 500s to high 500s, somewhere around there. They vary in price as much as they do in size. They get up to multiples of thousands if you start getting into the very large sizes, the largest of sizes. The largest I'd have is probably 32mm at the moment. The only reason I'm buying them up, I wouldn't probably buy them for a manual lathe unless you're doing 1,000 holes, or you've got holes of a set size that you're drilling all the time. They're definitely good for that. But the main thing is they're going to go over on the Mazak later on anyway, so I have brought a few sizes that I do plan on to run over on that machine. And I didn't forget to mention they have coolant through, which I'll take the actual tool out and show you the flow of coolant. I've had to upgrade the coolant pump on the lathe. Obviously, a normal coolant pump won't have enough pressure to be able to use a U-drill. You finish up burning up inserts. So I had to upgrade it from the standard 20 litre a minute pump to a 70 litre, which I'll sort of show you anyway. But most of you know that coolant pumps are pretty standard sort of things you see on bandsaws. I'll just show you an example of it. I'll just take it over to my bandsaw where I've got one on that. But as I say, we'll get it started up. One thing I did forget to mention was inserts, probably the next expense because you're burning those up. I'm not too sure of the 880s. I forgot now. I think the 880 style, which is the earlier version of the Sandviks, I think they only have 2 to 3. I can't remember now. Some different depending on the size insert. This has 4 sides, so it does get a bit expensive. As you buy more cutting edges, it's obviously more expensive. The more you get out of an insert, the more they charge you. You know, 3-point and 4-point inserts and things like that. You know very well when you buy lathe tools, things like that. The 2-point are cheaper than the 3, and so on, which is pretty common for lathe, and that's 2 and 3-point. But you can get 4 cutting surfaces out of this as long as you don't totally destroy it, rip the whole end off it, and then you lose one whole end. But you can flip it over if you're changing it over early enough. Probably cost is probably the downside. Tool and inserts. Tool I've already mentioned. Inserts vary from anything from, depending on grades and who you're getting them from, maybe discount might set you up better, but anything from possibly $15, $16 up to maybe the mid-20s per insert. So it's not too bad depending on how much you're doing, but for a CNC good, as I say, manual, it's totally up to you, but still worth doing on a manual lathe. The chips are a lot better, which I'll explain in a moment. I'll just take you over and show you the actual coolant pump for those who are interested, and just show you a little bit of the setup that I have, so I can help you if you wanted to set up something. Most of you are pretty familiar with this type of thing. You see them on cold saws and bandsaws. This bandsaw, which I've replaced, it's a new bandsaw, but I've taken the coolant pump off and put it on my old bandsaw because this is the pump that was on my old bandsaw, I suppose you could say. It's the same type of bandsaw. I'll show you shortly, just for those interested, what type of bandsaw I have. It's more of a tabletop version than the down on the floor version that most people are familiar with. But I've decided to swap that one over. Obviously I need to sell it, so I need to swap the actual coolant pump. So then the old bandsaw got a new coolant pump, and the new bandsaw got the old coolant pump. But the good thing about these is they're a lot heavier duty unit, and they're a lot cheaper to replace. The one that comes with it, I think they're around a bit over the 200 mark, and these are running, because they're such a common pump, I think those are around about the $120, $130 mark. The volume's about the same, but just when they wear out, and they do, the replacement on them's a little bit expensive. That's mostly why I bought this coolant pump to run on the other bandsaw, but I don't want to sell it with the other bandsaw because it actually had a problem when you actually swing the beam around, I suppose you could say, when you're swinging the actual bandsaw around and the angle, it actually hit here. So it's probably not, I can deal with it, but to sell it to somebody else, they probably couldn't deal with it. So the other coolant pump that's on the other bandsaw is probably a lot lower profile, so I had to make up a special base and everything like that because it's a lot taller pump. It hasn't got a really deep sump in here. But I'll just show you the actual bandsaw for those who are interested. So what I mean by tabletop version, try and get back a little bit. I've got some stuff behind me, so it's hard to get all the way back, but you've got this one where you're sort of more to your height, where you're working at your height. So the actual tabletop, I think, is around about 900 and something mil, so it's up where you are. I've got a plate on here rather than the segmented type of plate that some of them have, so it can actually shear through the part. I probably need to replace it at some point. It's starting to sort of wear out in the middle there, but what I mean by shear, you've sort of seen how a guillotine works, so it's getting the cut, it's not sort of, the part's not actually falling in there, which is fairly common with the bandsaws. They have normally a cast slotting in here, something you might be familiar with if you've seen this type of bandsaw. So I've put this plate on here. As you can see a few different cuts in there, but it actually shears through the part, so you don't get as much burr, and the part doesn't move as much too, because some of the parts I cut are fairly short and they don't get under the blade, because normally it's cast with a bit of a throat under there, so sometimes actually when it's cutting through, it actually drops into the fairly big hollow that's cast in this area here, and it actually gets under the blade and actually can probably possibly knock a tooth out too. So when they knock a tooth out, they're a pain in the ass. If you've run a bandsaw, you know very well what they run like when you've got a tooth missing. But anyway, we'll take you back over to the actual lathe again and get you started over there, and just so the more so chip control. There's probably the main advantage with the U-drills. Trying to do this one hand, it's interesting. You can probably hear the pump running. Just show you the stream of coolant that's coming out through the actual bore of the actual drill. This is where the advantage of, well, there's a lot of through coolant tools, but the U-drills, this is their main advantage. They flush the chips back out, whereas you don't get that normally with it. You've got twist drills that do have it, but U-drills obviously a lot better because you just got inserts to change rather than actually sharpening the drill bit. So you can see that stream there. So it's got a nice big stream of coolant coming through. It does get clagged up occasionally. That's one thing I do have to do. With this smaller U-drill, I find it does get blocked up with chips. So I have to stop it and then basically take it off and blow it back, flush it I suppose with some compressed air just to knock the chip out, because one of them stops working. And what happens is then if you don't have your coolant flow running, you finish up burning up inserts, which is not good. They're pretty expensive, doesn't do much for the part either, and it can ruin the actual end of the tool if you don't realise it. Probably not so much in manual because you see it, but in the CNC application where it's running in cycles, you don't notice it, and you can actually melt the whole end off it. Just some of you might have seen in some Instagram post or even on YouTube where the whole end of the U-drill is actually melted, where you haven't noticed possibly the tool's gone off or the coolant's not getting in there. But that's the good thing about it. It actually flushes the actual chips back through the drill, which I'll just show you anyway for an example. The other good thing is too, you see the chip sizes. Most of them are this size. Obviously on a CNC you can control the feed rate. I'm just cranking it through the tailstock. You get some longer chips at the start, these small spirals, but they don't wrap around the drill. And when you're drilling with a twist drill, you normally got your coolant nozzle pointing at your drill bit, and these chips always manage to whip around and hit your coolant, and you finish up the coolant more on you than actually on the part. Probably the main disadvantage, I suppose, is with the coolant wise on here. With the supply, you definitely need a good supply. You need volume. Pressure's obviously better, but in the case of this, with the setup that I have, I've got more volume than pressure. But obviously with volume, you're going to get some pressure, but it's not like a CNC where you're running possibly 7 bar or something like that. This coolant pump's anywhere near that, but it definitely gets a good supply, as you've just seen. But I run the lathe and just get it running, and you'll see the sort of chip sizes, and I'll explain a little bit more about it as I'm sort of getting into it, maybe some pros and cons of it. One thing is pretty much compulsory with a coolant through drill, or any type of coolant drill really, and if you've got it running on the outside of a twist bit, is a chuck guard. And I've put I suppose you could maybe call it a bit of a mud flap at the back here, so it's not whipping up and going out the back of the actual chuck. You can already see some marks on the wall there where the coolant's gone through. It's more so when the actual guard's open and the chuck's running more of a high speed, it's just flipping off all the grease and coolant that's still stuck in the chuck after it's been running. It does sort of hold in the actual jaws itself, so when I open the guard up, it will sort of get that propeller effect and coolant be going everywhere. So you definitely need some sort of chuck guard. So if you don't have one, you'll probably have to make one. It doesn't have to be steel, but obviously it'd be better. You can get one made out of plastic or something like that if you've got the capabilities of it, but definitely a chuck guard. It's more so the coolant that drains back out. It does hit the jaws, and it does get that propeller effect going, the coolant going everywhere. But I'll get you started. I can just show you a bit of a demo and just talk a little bit about as we're sort of leading in and we sort of increase the coolant as we're getting into it. It might be a little bit hard to hear, so sort of try to preempt some of it before I start the process, because it might be a bit hard for you to hear me over the lathe running if I've got anything worth adding to it. But just coming in slow, and I've got a variable tap, so it's just a variable ball valve, and I can control the flow. So I just start off at a low rate and then all the way open as I get into it. As you'll see the volume increase, and you actually see the coolant pouring back down through the flutes and the actual sides of the actual drill itself. You can probably see there, which will make more sense as I sort of get into it. They work their best when they're in the hole. They don't hold coolant very well when they're on the face. That's one thing about U-drills. You've got to get them in fast. That's where you lose a little bit of it. You probably, in this application when it's running on the manual machine, I can't run a massive amount of coolant because you've got to wear a raincoat if you try and run them how they're supposed to be run. In a CNC, you've got a cabinet around the machine. You just turn it on to your full pressure, and and then the tool comes in and starts, you haven't got a problem. But on a manual machine, you already know how bad it is with coolant on a manual lathe already without running a U-drill. So I've got you zoomed in pretty well, so you should be able to see everything going on anyway. As I mentioned, the coolant's on fairly low at the start because the coolant doesn't hold very well until it actually gets into the hole. Obviously the coolant needs to be flushing the chips out, and as you'll see, it doesn't really do a great job at the start. That's probably where on the manual setup it's not so great. As I mentioned, you've got to have a good flow with what I should say is get to the point of, with carbide, if you're running carbide, no matter what it is, inserts or tools, whatever, you either run coolant or no coolant. Don't run in between. But in this case, I have to run it because I'm deep down inside the bore. I'd probably go in about 90 mil. This U-drill doesn't quite reach all the way into the part, so I have to flip it over and come back from the other side. So I go most of the way up on the shank. But that's the thing is with it, you need to have really good flow of coolant if you're going to run carbide. So the chill factor of it, the tool getting hot and you cooling it down with coolant, interrupted coolant is not great for coolant, for carbide, as I say. So for those who know using carbide tool is nothing new, but for those who don't, yeah, it's either coolant or not. Either plenty of coolant or no coolant is generally the rule. But in this case, I can't run it without, because these inserts will probably last maybe 5 or 6 parts and I've already burned up one edge. So, but we'll get started and I'll just sort of get going with it. So getting started with a moderate stream, not really enough to cover, as I say, to cover the actual inserts, but it's all I can do. I don't want to put a raincoat on. If I turn it on a little bit more, you see it flooding up on the front. Just come in slow, let it face. Good thing about it is, which I forgot to really mention, I'll just turn it off for a second. Advantage of a U-drill over a twist drill, no spot drill, and you'll see the feed rate is you can just plunge in, whereas a twist drill, you're forever cranking back out, chip breaking, but with U-drills, you don't chip break. You just pound them in and let them cut. You don't need to chip break. Actually, U-drills hate chip break. And the other thing is, if you use U-drills, they don't like hollow bores either. You've got to go into solid material, otherwise you have to feed them in very solid. That's one other thing about U-drills disadvantage. They're not very good for through holes. If you've already got a hole there to go back in, U-drills don't generally like that type of condition. They like solid material to bore in. But it's a good drill to use to get ready for a boring bar. So just pecking in at the start, just trying to break off those. And as we get a little way in and get halfway down the insert, I'll just slowly increase the coolant. That's about probably 1/3 open, or maybe not even that. I'll just get the insert in, and then we wind up the coolant. As the drill starts entering, so basically it'll start following that channel as we get further in. You guys can fast forward if you like, it does get a little bit boring. So you'll see the actual coolant as it gets into the straight part of the flute. It starts to make like a canal, or a channel I suppose you could say, along the drill. Imagine trying to just keep plunging in for a twist bit. You'd have a piece of swarf as long as your body hanging off there, but with U-drills they're chip breaking themselves, so you don't finish up with those long streams of chips. Because I'm feeding that by hand, it's a bit erratic, and if you're feeding it with CNC you can keep your chip load a little bit better so your chips are a little bit more consistent. But it is what it is. I'll just pause that and come back. Just coming back, you can see the amount of coolant that's going in there. That's a good thing about it, it's back flushing, so you've got your coolant at the tip. I mean, most of you have even watched CNC mills or lathes, whatever it might be, especially on mills, you have through coolant, and that's the big advantage of having through spindle coolant, is you get the actual coolant up at the cutting edge. Just turn that off now, and what I do is I just turn the part around and drill the other end then. Just turn the coolant pump off, gets a bit drainy. But yeah, probably the cost is probably, the setup cost is probably the worst part, and obviously setting up your tools probably but once you're up and running everything, it's not too bad. But as I say, I probably wouldn't do it on a manual thing for ongoing, as I say, unless you've got plenty of holes to drill of the same size. But they are good for starting to do, if you want to put, if you're doing something, you just start off with say a size like this, and you just get in just to start out your material, and then you get in with your boring bar and then chop out your material. They're definitely better than using a normal twist drill. Just bring up a handful of chips. This is where their advantage is. So look at that. It's, you know, the chip sizes, you know, some of the longer ones are probably when I'm entering more so, but as it starts getting into the actual job, it starts to see how long those chips are. That's pretty much how it's breaking the chips. So it just strings them out and then snaps them off, and they just keep pouring out. Because you're going to get different sized chips too, because depending on the material, it's going to operate differently. But the good thing about it is just it's pushing all the actual chips back out from the cutting face, which you pretty much can never do with a normal twist drill. You're down the bore and you're flooding coolant in there, but it's not actually getting to the drill. You're doing your best you can, but you're still cooking the actual drill bit anyway. That's running at about, I think, just under the 600 mark, 600 RPM. So that's a good thing about it too. Imagine trying to run a twist drill at that speed. You just cook it, you know, with high speed stills, nowhere near it. And you can, the feed rate just plunging in without coming out chip breaking and twist bits coming out. But that's all the positive. The negative, setup and cost. I suppose that's the worst part of using this type of drill. But once you set up and the money's spent, and you can just bore into a part, they're great that way. But I just thought I'd include you guys in on this one. Thought it might be something information worth sharing. As far as using U-drills, I don't see a lot of guys using them on manual lathes, probably because the fact of cost is more so. But you don't need to buy every size available. But you can just buy one set size and just use it as your pilot, I suppose. And then you get in with your boring bar and just start cutting. And it's a lot better than a twist drill. But and once again, cost. Every positive has a negative, every negative has a positive. Otherwise, that'll do for this video, and I hope you guys enjoyed it. I'll see you on the next one. Okay, bye for now.